I'm just waiting a moment to let people come into the webinar, and then we'll get started. All right. Hello, everyone. My name is Tina Grotzer, and I'm the faculty director of the Next Level Lab. I just want to welcome you to today's event and express my gratitude for this community. And then I'm just going to turn it over right now to Megan Cozzolino, who's the project director of the Next Level Lab, and she will orient you to today's session.
Thank you, Tina. Hi, everybody. As Tina said, I'm Megan Cozzolino. I'm the project director of the Next Level Lab, and it is my pleasure to welcome all of you to today's Next Level Lab speaker series presentation with Dr. Mohsen Moghadam. In a moment, I'll be turning it over to Dr. Chris Deedy, who will introduce our speaker. But first, I'd like to just say a few words about the lab and share some logistical details about today's session. Launched with funding from Accenture Corporate Giving. We leverage and contribute to research in neuroscience, cognitive science, and the learning sciences to enable new possibilities in developing human potential and to create greater access for vulnerable, underserved populations. We adopt an expansive view of learners as embodied cognitive, emotional, and social beings, as situated within complex contexts, and as needing to know how to engage their minds and the malleability of contexts towards their best learning and performance. Very importantly, they need to be successful in a world filled with volatility, uncertainty, complexity, and ambiguity. Learners need to learn throughout their lifetimes and navigate changing terrain over the course of their careers. As a small lab, we view our mission as one of inviting conversation, providing purpose, and offering guidance to the field, with this speaker series as a part of that effort. So to that end, we are delighted to be welcoming Mohsen Moghadam to the speaker series today. We expect that there should be time for several questions at the end of the presentation. So please submit any questions you have using the Q&A feature in the webinar, and we'll share them at the end as time permits. We'll be closing the chat during the talk, so if you run into any logistical issues, you can also put those into the Q&A box. And with that, I will now turn it over to Chris to introduce our speaker.
So I'm Chris Deedy, a senior research fellow here and a senior researcher with the Next Level Lab. I'm delighted to introduce Mohsen, who's an assistant professor of mechanical and industrial engineering at Northeastern University, as well as an affiliate faculty member in the Curry College of Computer Science. He's also a visiting scholar this year with us at the Next Level Lab, and he's co-founder of ADA Tech, Advanced Design Augmentation Technologies, a new startup dedicated to augmenting early-stage design processes through AI. He received his PhD in industrial engineering from Purdue, served as a postdoctoral researcher at the GE Purdue Partnership in Advanced Manufacturing. His lab focuses on exploring human-centered computational models, algorithms, and tools at the intersection of AI and spatial computing to enhance learning and creativity in various industrial settings. And his work is of great interest to NSF, DARPA, the US Navy, Northeastern University, and industry, because they all provide funding for him. As on a more personal note, I will say that I've been working with immersive technologies for more than 3 decades, find them to be very powerful. And I'm excited about Mohsen's work and very much looking forward to his talk today. So Mohsen, over to you.
Well, thank you very much, Tina, Megan, and Chris, for very kind introductions. And thank you for the opportunity. And good afternoon, everybody. Happy Valentine's Day. Thank you for spending your time with us. I'm going to spend probably 40 to 45 minutes talking about some of the research that we have done over the past few years, mostly focusing on our recent and ongoing work, and hopefully we'll have enough time for Q&A. I would like to start my talk today with one of my most favorite quotes that I'm also not quite in agreement with. the first time I saw this, I was an undergraduate student. It's a quote about a man and a dog in a factory of the future who are the only employees essentially doing nothing. So back then, as an engineering student, this quote really struck me as something positive and cool and futuristic. It's like lights out production, all about automation and machinery, and I'm an engineer. But as I grew more in research, I gradually started to understand and see the downside of pushing for automation that tries to minimize and eliminate humans from these processes. Because I personally believe, and I'm pretty sure that the learning sciences community mostly believe that there's much more to what humans can do and contribute than just feeding a dog. Metaphorically, I'm all for feeding dogs, but not like this. And there are certain things that can't be, or maybe even shouldn't be, automated or replaced by machines. And examples of companies like Tesla failing to hyper-automate their factories serve as a proof of this very fact that humans are needed and are very much relevant in these kinds of industrial workspaces. Even though we still see examples of more emerging technologies, from self-driving cars to AI, now large language models and so forth, still being very much laser focused on this notion of reaching and competing with human level capabilities and potentials to hopefully in the future somehow serve humanity, we hope. But none of this, at least in my opinion, means that this is the end of human role in future work. This is simply another chapter of our evolution, at least in industrial, in workplaces. All of us have heard this idea of automation creates jobs, destroys jobs at the same time. And that is in fact true. And it's actually backed by a recent study out of MIT Econ that is based on data from over 300,000 firms. The study shows that industrial workers, especially manufacturing workers, are more exposed to advanced automation technologies than ever before. And in this context, exposure means working in firms that actively adopt advanced technologies such as AI, robotics, automated equipment, not including robotics, but machinery, software, and cloud computing to automate jobs, to basically replace humans. But despite all of these alarming numbers that you see here, from 30% industry average exposure to over 50% in manufacturing, not only does this study show that the future will not be fully automated, fully lights out, it actually predicts an increasing demand for skills, but for high-tech skills, skills that are required to operate and work with, operate, troubleshoot, maintain these advanced machinery, software, and systems. So as a lab, our vision, our very overarching vision here is to build computational tools that serve as intelligent companions for humans in these industrial future workplaces. And our vision, our perspective here is that the future will require more complex, psychomotor intensive, and cognitively challenging tasks. So our goal is to build these intelligent companions that are at the intersection of extended reality technologies and AI to help humans develop those skills and also perform these complex tasks more effectively. But this loop that I'm showing here in my slide, new technology pushing humans and also workplaces to adapt to the new technology, this is not new. This cycle has been around since technology, since the very, at least since the very first industrial revolution. But the problem is that modern technology is growing so rapidly nowadays that it's becoming increasingly more and more difficult for humans to keep up with that. So, and that not only applies to manual work anymore, it actually applies to cognitive tasks such as programming. And there are also news and some predictions that even extremely cognitive tasks such as computer programming may actually end up being to some extent automated over the next few years with the advent of these large language models. So in a nutshell, our vision is to basically help humans adapt to these new technologies and basically fast track and accelerate this kind of adaptation. Whatever that means, it depends on the work context. I am personally interested in industrial workplaces because of my background and because of my interests. So in that case, that will basically mean workplace-based learning and industrial training and on-the-job assistance in manufacturing industry. So, but why is this important? Why? I mean, most of the projects that we have, active projects that we're working on in the lab, are related to some form of industrial training. And as you probably know, skills gap right now has always been a kind of like a wicked problem in the US workforce. And it also is driven by more than one factor here. Retirements of the baby boom generation. They're rapidly retiring. There are predictions that a major population of the baby boomers will be retiring soon. The new generation is not most excited about manufacturing work because there's still those misconceptions about manufacturing. Training, there's a lack of systematic approaches for industrial training in the manufacturing industry and all other industries, specifically in manufacturing. Tribal knowledge is an issue. My colleague Alicia Modestino and her team are now conducting interviews with different manufacturing firms here in Massachusetts. And this is one of the issues, that there is a lack of systematic approaches for industrial training. When they bring a new piece of machinery, there's always this one of those, or some of those smart workers who figure the machine out, and then it becomes kind of challenging and very dependent on those workers. And they usually don't want to share that information with the rest of the team, at least not completely. And as the MIT studies show, technology is also playing a huge role here. In terms of, because the introduction of the new technology is making future work more advanced, more sophisticated, that will require more and more training. And as a result of that, there's a prediction, these numbers vary from year to year, but there's a prediction that over 2 million jobs will be left unfilled by 2030 in the manufacturing industry. Manufacturers are increasingly reporting difficulty finding skilled workforce. And women and minorities are underrepresented in the industry and are much more likely to leave it as a result of a lack of systematic approaches for training and also for retention of these workers. So considering all of these, this is the overarching problem. This is the fundamental problem that we are trying to address through our research on XR and AI-enabled XR for workforce training and on-the-job assistance. So the fundamental question that we're asking here is that, as I already mentioned, how can we accelerate this progression? Because these predictions show that in the future, there will be more demand, but that doesn't mean that there won't be supply of people. There will be this mismatch between what those people are capable of and what those jobs require these people to perform. So the overarching question that we're asking here is that how can we accelerate the progression of novice to experts in these future high-tech industries that require more psychomotor intensive and cognitively challenging skills? As Chris mentioned, XR has been, over the past couple of years and decades, has been considered as one of the a very strong tool for industrial training, because of the very fact that, and it goes from VR all the way to AR. So XR is an umbrella term that is used to refer to a combination of virtual reality, fully immersive environments, all the way to augmented reality, which is you see the physical environment, but you also have some content superimposed on the physical environment. And it has been used extensively in industry for training. And one of the main reasons for that is the spatial temporal alignment of instructions with the task. In the case of VR, you're immersed in a fully immersive environment, and you can interact with different objects. You can have a spatial understanding of the task and on the objects within that work environment. And in the case of augmented reality, the provision of those instructions right here in front of you on the machine actually has been shown to help in terms of improving performance, in terms of reducing errors, and so forth. Here's an example of a project that we recently completed. We're almost close to completion for the US Navy. In this project, we created a full-fledged XR system from fully immersive virtual reality system all the way to mixed reality and augmented reality system for 2 industrial training use cases: cold spray additive manufacturing and robotic painting. Here, what you see here in the video is one module of the training, which is basically preparing this powder feeder for metal additive manufacturing. In the case of VR, the user goes through the process using controllers. And in this case, we use MetaQuest and HTC Vive. In the case of AR, we use HoloLens. Here's the example of the AR and VR training systems for robotic painting. And as you can see here, in all of these examples, you see different instances of information delivery from text all the way to video to immersive animations, and all superimposed and provided on the job in front of you as you need it. And examples of these there are many projects out there, and we are not the only group, obviously, that have studied different versions of this, have evaluated different versions of VR and AR training for systems for industrial use cases. But the issue is that this is great, but based on our research, and that was actually the start for us, the majority of this community of industrial AR, industrial XR, industrial virtual reality and augmented reality has been predominantly focused on building the technology itself, like these projects that we perform for the US Navy. And that goes from building the animations to tracking, registration in the case of AR, automating authoring, and so on and so forth. And that's for good reason, because the technology is the backbone of industrial XR-based training. But one of the limitations, or I would say one of the gaps in this literature, is that there is this implicit assumption that these systems, these VR and AR systems, automatically lead to better learning, even though there hasn't been much evidence. There are some evidence, but there hasn't been much evidence on studying different versions, different variations of these systems with respect to learning effectiveness and how to optimize for that. So that was the start for us. And in order to understand this gap a little bit more, during COVID, and you see these subjects are wearing masks, we decided to conduct an experiment, which was based on a real-life assembly module. This is a fuel cell of a marine engine that we work with a manufacturer in Massachusetts. And we created an augmented reality application for it. We brought subjects to the lab, and the task was a completely procedural task. Some of the steps could be done in different orders, but we already had the task model and instructions for the subjects. And in this case, we wanted to basically study the effectiveness of AR, mixed reality in this case, in terms of training. So we hired two groups of subjects, and we did a between subjects design, and we had an XR group and we had a paper group, and we brought them to the lab in 4 rounds. And the XR group received AR instructions, XR instructions through the headset for the first 3 rounds, and then we swapped the mode of instruction between XR and paper. The main reason here was to give these students the opportunity to use HoloLens, but we also found out that we also came up with some interesting results here. So the results of this study showed that in terms of time, in terms of independence, which is the number of questions they asked and how much dependency they had on the experimenters, and also in terms of cognitive load and self-efficacy, both groups were about very similar to each other. So we didn't really notice much difference. But the main significant difference that we noticed was the number of errors. That both groups had a relatively large number of errors, as you can see in round 1. But as they came back and repeated the experiments over and over, the XR group showed significant improvement in terms of the number of errors they made, while the paper group still made those mistakes. And those mistakes were like missing the parts, or mixing the parts together, or not completing the instruction, not completing that step in terms of screwing things and so on. And they were overly confident, especially the paper group, because these were all engineering students. This was someone confidently doing something incorrectly. So the findings showed that XR does indeed enhance learning, spatial reasoning, and retention, but something else was missing here. So the nature of questions they asked and the help-seeking behaviors and the kind of errors they made really made us think that something else is missing from this system that has been around and studied for decades in the learning sciences. And of course, we owe this to our learning science co-PIs, Kemi Jonah and Nick Wilson. And that was the one-size-fits-all nature of these systems. And we hypothesized based on that the one-size-fits-all nature of these training systems that are like, in many cases, even Microsoft Dynamics 365 is like an immersive PowerPoint, that you are fully in charge. You need to tell the system what information you need to navigate through different steps. And the system does not have much intelligence in terms of adapting and tailoring those instructions to you. So we hypothesize that the one-size-fits-all nature of these instructions actually does not serve learning in terms of learning effectiveness because of the very fact that it completely ignores the learner and what is happening in the environment, and it does not have the capability to tailor the instructions and tailor the experience to the user. So to better understand this, we recently, last year, we conducted another study, in this case on a precision inspection task. And we have these manufacturing use cases because that's the focus of our NSF Future of Work grant. So in this case, we designed a precision inspection task, and we proposed that an XR system that is combined with an intelligent tutoring system would increase learning effectiveness. In this case, we had 3 subjects. We did between subjects design again, but in this case, all treatments received XR support. But in this case, we had 3 different conditions. We had full scaffolding, on-demand scaffolding, and adaptive scaffolding. The full scaffolding group was required to go through the instruction. So it was a procedural task. They had to review the instruction associated with step 1, then complete the step 1, then go to step 2, and so on and so forth. The on-demand scaffolding group, however, had the option of choosing to, they had the option to review the instructions. They were not required to do that. So if they were really confident that they know how to, for example, perform a certain step of calibrating a gauge or cleaning the gauge or turning it on and so on, they could skip it. They were not required to do that. In the adaptive scaffolding group, for the adaptive scaffolding group, we created a relatively different version of the AR system where the interventions were provided by a PhD student behind curtains. That was like basically our wizard that used coded rules and real-time text-to-speech generation code to provide instructions and interventions in real time and sound like a computer to the subject. So the participants didn't know that there is a PhD student behind the scene intervening when they make a mistake or when they forget something or when they're stuck and don't know what to do. In this case, we worked with 30 participants from our mechanical industrial engineering program and also from Mass Bay Community College. And the metrics were number of errors, cognitive load, basically NASA TLX, and self-efficacy. And the results of the experiments showed pre and post intervention that the adaptive scaffolding intervention significantly improves task performance and learning. In this case, task performance is measured in terms of the number of errors they made post-intervention. So we had them do certain tasks pre-intervention, then they received their own version of AR training, then they came back for a final test without any AR support on different variations of the tasks. And the experiments actually validated that adaptive scaffolding, when you tailor the instructions and interventions to that particular person's experience, the kind of errors they make, and to the information that at least we believe, or the wizard believed they need, they learn better. And that better is measured in terms of the number of errors they made during the test. So that kind of validated our hypothesis. This is the core of my, and I should move a little bit faster. This is the core, the main slide that I wanted to get to. So all of these led to this intelligent XR framework that we've put forward. This is the core idea behind our NSF Future of Work grant, and we also have a recent NSF funded by RIDL, grant funded by RIDL, that is a continuation of this research. So in this case, the fundamental question that we are trying to address is that how can we turn XR into an intelligent companion, into an expert that looks over one's shoulder and has a good understanding of what is going on within that scene in front of the person, what activities that person is performing, have they made any errors, are they doing the right thing, are they doing it right, and so on. And that is basically the data-driven activity understanding module. The expert, that this virtual expert, the intelligent companion, should also have a good understanding of the metacognitive state of the user. Like, how are you overwhelmed? Are you cognitively overloaded? How good are you in performing this task? Do you actually need help? Should I help you, or should I just get out of the way, right? And that is the data-driven user modeling module of this. And then both of these modules feed their inferences, basically the decision they make based on the data collected from the outside and from the inside, and feed that into an adaptive inference and intervention engine that generates those interventions. And our approach here is going to be fully data-driven, and especially because these headsets and some other wearables, from brain-computer interfaces to wearables that are used to collect your physiological data, egocentric camera, exocentric camera, and also machine and IoT data, can help us make these decisions and these inferences more accurately and in a real-time and online fashion. So for the rest of this talk, I'm going to talk about examples of our work. Some of them might be a little bit technical. I have cited the papers, and I'm happy to expand on those offline or during Q&A. The first module that I want to talk about is data-driven activity understanding. And by the way, this is motivated by that idea of the wizard. So once we create this system, this intelligent companion is intended to function as the wizard that I talked about in the previous slide, that we show that it can effectively improve learning compared to other traditional ways of providing instructions in AI. I'm going to skip this. This is the analogy that I use to explain this, but I think I've already explained it enough that the state-of-the-art industrial AR, XR for training and assistance, if you want to really draw an analogy between navigating through a task graph to provide like instructions in terms of a procedural task to a person, if you want to like use an analogy of that being analogous to a road, in this case, the traditional approaches are more like a paper map that you are fully in charge to tell it exactly where you are on that road. But in the case of a navigation system, the navigation system always knows where you are. So in terms of activity understanding that I mentioned here, you can think of it as a GPS, but as a GPS in terms of task performance for the system to know exactly where you are. Have you made the wrong turn or right turn? Are you on track? Are you off course, on course, and so on? And the user modeling aspect of it, not even the navigation systems have that. You can think of it as like a hypothetical feature of a Google Maps navigation or some other navigation system that also tailors the instructions to the driver. For example, if I'm an expert driver, it says, take that exit. If I'm a novice driver, it provides more scaffolding, more support that, hey, don't forget to check your mirrors, gradually switch lane, and so on and so forth, right? So I have some examples of activity understanding. Here's an example of a work that we recently did related to activity understanding for egocentric hand action recognition. In this case, we use hand skeleton data collected from the headset, from the depth sensors HoloLens headset, to enable real-time and online hand action recognition. And in this case, we are building on some state-of-the-art literature in computer vision, where the focus here is mostly on building something that is a little bit more efficient in terms of inference time and speed, and more accurate than state-of-the-art. And here we also created a data collection pipeline for other researchers if they want to build this system for other use cases. They can to basically avoid the need for manual annotation for data for the data that they need to train their system on other use cases and on other data sets. So in this case, we developed a machine learning architecture that is at a very high level based on temporal graph networks that are basically temporal convolutional networks and graph convolutional networks to, in simple terms, capture the temporal and spatial aspects of the data. In this case, we're talking about 26 joints of someone's hands, and these tasks have a very strong temporal aspect to them, because when you perform something, detecting what is happening now depends on what happened a few milliseconds ago, a few seconds ago, and so on. And we also did some feature refinement using contrastive learning. I really don't want to dive deep into the details of these, but long story short, we have developed a system that can use the data captured through the depth sensors in front of which are like built into all XR headsets for hand action recognition. And in this video, you see that it is quite responsive. Of course, we don't want to show this to the user, but it is quite responsive, and it makes those predictions. You're attaching it, detaching the gauge, and so on. We had about 16, I believe, different classes here to do hand action classification. This is useful because this, in conjunction with other types of data and other models, would actually help us make more inferences about more higher level, more complex activities, or even for a step detection. And I have an example of that. In continuation of what we did there, this is an example of step and error detection work that we've recently done based on the inferences that come from the hand action recognition module that I just showed you, with IoT data that we capture from the parts and from these digital gauges. So we put very tiny IMU sensors on top of inside the 3D printed parts and on the gauges to stream in real time data from the gauge and from the part to the system. And as you can see here in the video, for example, if I go a little bit back, let me first explain this and I'll play the video. So in this case, the idea is that I can do hand action recognition. If I can pull some IoT data from the part, in this case, the IMU sensor basically tells you whether the part is stationary or is moving. Same for the gauge. The gauges are also wireless. You can communicate the readings of the gauges through the pipeline to the headset to make inferences, to see whether what you have measured or whether your measurement is correct. And in this case, we also have the task graph. So we have built a rule-based method which receives the hand action recognition inferences from the module that I showed you in the previous slide, with the data that come from the parts and from the gauges, and following very simple rules that always check for completion criteria for each of the steps, tell you exactly where you are in that task, and have you made any mistake? In this case, the mistake that we can catch is in the form of missing a certain step, okay? And here with the task graph, the task is basically using this caliper to measure a simple part. And as you can see, these are the steps. This is for calibration. We won't be showing this to the subject, but as you can see, it has it when it marks it green, that means you have located the caliper. The caliper is on. Now, as soon as you switch it to inch mode, this should turn on. So the system knows that this step is checked. Now, the next step is to wipe clean it before you calibrate it. But here the student intentionally skips that step. And as you can see, when you start calibrating it without wipe cleaning it, it throws out this error that, hey, you forgot. Of course, we can add more interfaces, like notification interfaces. And as soon as you do that, it's satisfied that that condition is met now. And then you can continue throughout this process to perform the task. This is, again, this dashboard is just for our calibration or for our demonstration. We are working on building an application that basically acts upon the inferences that come out of this system, that, for example, if you miss something or if you forget something, it throws out some notification, or it actually tells you in real time, the same way that the wizard would do, but in this case, completely automated. And here the student can also just rotate the gauge and use the speech to record the data, and the data is automatically recorded to the system. And if it's and then the system can take actions based on that. So this shows that it is promising in terms of helping us detect the steps, and also in terms of helping us detect some kinds of errors associated with missing the steps or forgetting something. But this, of course, has its own limitations because it's rule-based, and it is relatively expensive because you need to put sensors in every single component that you have in the system. An alternative approach is computer vision based, in which the computer vision community has been extensively working like in that space. And we have done some work in this area. One of the students is working very actively in this domain. The idea here is to just use the RGB streams and the egocentric data that come from the headset to segment the actions, to detect what actions are happening. In this case, it's an offline model, but you can also do it in an online fashion. We have done this, we have built a system that is based on transformer-based architectures. I can expand on it if there is anyone interested in this domain, but in a nutshell, these transformer-based architectures are the backbone of common things like GPT or like these vision language models that you see out there, that they understand the temporal context, they understand the context in the data. Okay, so in this case, as I already mentioned, in activity understanding in general, there's a very strong temporal component, and therefore these models work like show some very promising performance in terms of detecting the actions. And we have made some improvements to these models to increase the accuracy. But the bottom line that I wanted to show you is that even in this case of a data set that you train it, you test it, validate it on the same data set, it's not online, it is offline, and so on. Even in this case, the accuracy is not that great. It's actually around like 70 to 80% accurate. And if you take the same headset and put it, the same model, excuse me, and put it on a different data set of making tea, it may actually end up performing much worse than that. And if you make it an online system, it's going to even like underperform significantly. So the message here is that computer vision itself, like alone, is not enough. And that's why the previous slide and what we have done so far is our golden approach in terms of activity understanding at the moment. Now, I want to quickly switch gears and talk a little bit about the other two modules because it's already 3:38. The second module, so that was about the data-driven activity understanding. These are some of the work in progress that we're doing, but in a nutshell, the point of data-driven activity understanding is to detect actions, steps, and errors that a person, basically whatever is happening on the outside. Data-driven user modeling, it is very important because at the end of the day, especially in the kind of research that we do, it is what I already mentioned, the IXR framework is going to be serve as an intelligent companion, right? In order for this intelligent companion, this mini expert that is sitting inside the headset or over your shoulder, looking over your shoulder, it needs to know how good you are. You need to know, in order to tailor the instructions and interventions to the user, you need to have a good understanding of their level of expertise, not at a task level, but at the much finer grained level of specific actions, or at least steps of that process. This is a research that is sponsored by DARPA Perception-Enabled Task Guidance that another student of mine has been working on. 2 other students have been working on. And in this case, the question we asked was that, can we use the gaze data that we can capture from the headset in conjunction with object detection through computer vision to come up with a model that gives us some estimate of the person's expertise. And this is actually informed by the literature. There is extensive literature, especially in the medical domain, that is based on the I-mind hypothesis that your visual fixation is correlated with your mental cognitive processes, and also information reduction hypothesis that states that as you become more expert, you intentionally tend to fixate on relevant areas of information. So the tasks are making coffee and pinwheel. These were dictated by DARPA as usual. So we didn't have much choice in terms of the tasks. And some reviewers actually criticized that, these are relatively trivial tasks. But the idea here is that we used gaze data coupled with object detection and the correlation, basically the overlap of the gaze and the bounding box of that object, to have some to estimate, to not to say it precisely, because there is some noise in the data, as you can see here, to tell what object the person is looking at or fixated on, or whether the person is fixated or not, to then study the relationship between their fixation and saccade duration, visual attention, scan path, and gaze sequence. And pupil size dilation wasn't much informative here. Between that and their level of expertise. So here we also ran a small user study. We are redoing this user study with a better hardware now because the data was kind of noisy. But the results of our preliminary user study showed that experts, we also validated those hypotheses basically in the literature, that experts, if you're an expert, you tend to fixate longer on relevant areas of interest, and you have more stable fixation. You don't jump between different objects in the scene. And based on that, we have developed some simple rule-based models that then receive the gaze data in real time and come up with some estimate of that person's level of expertise. This again, like this is a work in progress, and we'll be redoing these experiments. But overall, it sounds promising and it works, but there's a lot more to be done in this space. But this is an example of expertise. As we continue to work on this, we thought that even if this system works 100%, at the end of the day, it tells you how good you are in terms of your familiarity with the objects in your environment, in terms of familiarity with the scene. But the problem with that is that this is just one aspect of expertise. And the hypothesis here is that expertise is indeed, not hypothesis, based on the literature, expertise is indeed multidimensional. There are different dimensions, different aspects to expertise. And the example that we use usually to explain this is that, for example, the surgeon and the surgical assistant, both of them, based on this previous model of expertise, both of them should have very high level of expertise. Hopefully, they should be familiar with the objects in the environment as they perform the surgery, but only one of them is qualified to do that, because in addition to that, there's also other dimensions, other aspects of expertise that are necessary for that person to perform that complex cognitive and also psychomotor task of surgery. So this is a work in progress. We have a pipeline set up that one of my students, that's Steven, flying a Cessna airplane in Microsoft Flight Simulator. And we have completed the pipeline. In this case, we can capture physiological data, gaze and pupillometry, GSR, and controller data. And through using iMotion software, we have synchronized this. And we are in the process of designing a new experiment to first and foremost test the hypothesis associated with different dimensions, different aspects of expertise, from technical proficiency to domain knowledge, decision-making, situational awareness, and the person's cognitive load and stress, to see if the hypotheses are indeed valid, and then based on that, develop multimodal data-driven models to estimate the user's level of expertise. This is a work in progress, but this is the vision that we have for this. And related to user modeling, this has been our primary focus. Other researchers, other research groups with whom we interact as a part of the DARPA project are more interested in cognitive load detection. But this is our main focus, because this is at the end of the day going to be an intelligent companion. In the interest of time, I need a few more minutes, and then we can open it for questions. The last piece is the adaptive inference and intervention engine. I'm just going to show you some quick demos of what we have done. In this case, we have built a domain-specific dialogue system. I'm not sure if you can hear the audio, but in this case, what we have done, long story short, we have built a dialogue system that is based on a large language model, fine-tuned on the document, which is the operations manual, maintenance manual, documentation, on a very large document that we assume contains all the information related to that particular task, so that within AR, the user can initiate a dialogue with that fine-tuned large language model to answer any question they might have related to their experience. And here is a demo of that. And it is, again, the pipeline is ready. We haven't done any testing on this, but first of all, we're going to improve the performance in terms of question answering, and then do some user study to see if this actually helps. And the last demo that I wanted to show you very briefly is that here the vision is to extend everything that we have done so far to a human robot collaborative scenario, where we have a robot and a human working collaboratively on a psychomotor task of assembling something. And in this case, what we're interested in is to study different communication channels, different ways of communicating with the robot through augmented reality, and also receiving confirmation through the system that this is what the robot understood. This is the robot's understanding of your intent. So in this case, you can use your gesture and gaze. You can use your gaze and speech, or a combination of different, more intuitive, like in this is an example of gesture that you can pick it up through the sensors of the headset, and it goes through a pipeline to the robot program and activates the robot. And then the robot, once it receives that message, sends that message back to the augmented reality headset, and you receive a message from the robot that this is what the robot understood from what you asked it to do. This is in the making, but the overall plan for this is to basically bring whatever we wanted to do in the context of fully manual tasks to human robot interactive tasks, and there are good reasons for that. Just to wrap it up, the idea here is to the next step for us is to integrate all of these different modules, and I can expand on it and also validate, do more validation across the board, from activity understanding to user modeling to inference engines, and work on generalization across different domains. In closing, this is what I started with, that this is the overall, the main vision of the lab. And this is what we've been working on. But there is significant interest from NSF and other agencies in terms of studying co-adaptation and co-learning in these kinds of environments. There are some calls, and of course, there is good reason for that, to consider differently abled individuals in these use cases. So that's another potential interesting idea for future research in this domain. And considering this as a system of machines, as a system of headsets and users and machines interacting as a part of an ecosystem is also another potential direction for future research in this domain. And last but not least, of course, other contexts. So far, we've been heavily focused on manufacturing, but there are any psychomotor tasks that involves mind-body coordination and some decision-making, and for which we need to train more and more people, would qualify to be considered and studied under as a part of this framework and this line of research, with like through us or other research groups interested in this. And finally, the brilliant PhD students and master's students and my wonderful co-PIs on all of these projects, I wanted to acknowledge their contributions and thank them for all the hard work they've done so far over the past few years on these projects. With that, I'm going to conclude and open the floor. Hopefully we have 11 minutes. Thank you so much for your attention.
Mohsen, thank you so much. I really appreciate what a difficult task it is to communicate such a rich and complex body of research in such a short amount of time. So thank you for putting it all together for us. We do have time for some questions. So I'm really pleased to be joined today by two of our research assistants in the Next Level Lab, Hua Yu and Yufi Liu, who have graciously agreed to facilitate this Q&A portion of the session. So Hua, I'm going to turn it over to you to pose the first question from our audience.
Thank you. And thank you, Mohsen, for a really thought-provoking presentation. For our first question, we have from one of the attendees: how do you think about communicating the opportunity of this technology to folks who might be a little bit hesitant about adopting it?
That's a great question. And let me see if I can remember what slide it was so that I can jump to that slide, slide 4. So that's a great question, and I forgot to mention that actually this vision is heavily influenced by the NSF Future of Work at the Human Technology Frontier program. That was one of NSF's 10 big ideas launched back in 2016, 2017. And under this program, we have 3 main dimensions, and they also want us to come up with a work context, and that's why we've been heavily focused on manufacturing. One of them is future technology. The other one is future worker. That is mostly about, in our case, the learning sciences aspect of the project. There's another component, which is future work. And my colleague, Alicia Modestino, who's a labor economist, has been working extensively on that front. And one of the challenges we've been facing, of course, similar to any other technology, I'm not sure if you have read the literature or like the stories about when robots first emerged in industry, there's always resistance, there's always hesitation. And let me see if I The opportunity is there. The challenge right now is that hardware is still a little bit behind. With headsets like Microsoft HoloLens, I don't really envision that being used in industry at scale because of the very fact that it's very expensive. It requires maintenance. It's not a robust headset. It heats up. You can't wear it for more than 20 minutes. Maybe as an assistant, yes, but as something that you wear all the time, no. And the other challenge is privacy. Like, because like what I've been talking about, what we have been talking about so far is like having someone looking over your shoulder. It's very difficult sell to those unions that, you know, let us put these headsets on people on the shop floor, and you can always basically control and monitor them exactly what they're doing. And then the idea of activity understanding is like every single action you perform, the system can pick it up and label it and store it somewhere, right? So privacy is an issue. Hardware is an issue right now. Privacy is another issue. And lastly, I think, but one thing that I'm really hopeful about is that this is something that I'm personally interested in, is I really want to develop technology that serves people and augments people rather than replace people. And I expect this to be in that case an easier adoption compared to something like a robot or some software that would basically eliminate some jobs. I hope I answered that question, and if you're I'm happy to answer any follow-up questions about that. But that is part of Alicia Modestino's research, and I'm happy to connect you with her and her research group about that.
Thank you for answering the first question, Mohsen. I also really enjoyed your talk. I think it was very informative and very impressive. We also have another question from Tessa. She asked, I'd love to know how you think analysis of this kind of data might change in the future with generative AI.
Could you repeat the question? I'm not sure if I see the same questions here.
Oh, yes. Tessa asked, I'd love to know how you think analysis of this kind of data might change in the future with generative AI.
Oh, with generative AI, that's an excellent question. So with generative AI, maybe nine. So with generative AI, this part specifically, because these two, you can think of them as classification or regression problems. Okay, so data comes in, and based on that data, tell me what step is happening. That's a classification problem. Or based on this, tell me how good the person is. That's a regression problem. So mostly in these cases, these are supervised learning problems, the first two, that receive some input and generate something as the output. The interesting component here is right now we have developed the system that we have in place is relatively rule-based, right? So you receive the inputs, and based on that, you follow certain rules and generate certain outputs, interventions, right? But you can think of this as, and this is the task domain knowledge, the dialogue system that I mentioned, that this is, you can think of this as a very large PDF. And right now there is a significant amount of work on question answering from PDF, or like using large language models to make sense of these large documents, right? So the inference is that the data that you have here in your domain task domain knowledge database, knowledge base, and the inferences that come from these two modules can be combined, and then you feed it into a generative AI model. And that generative AI model could generate text, generate image, generate anything, generate videos, maybe in the future, or generate content in your 3D space. And in our case, generate interventions. The question is like, can you build an AI that generates instructions on the fly? I mean, we have the components that would feed that AI, that generative AI, but the question is, how do we design that generative AI that actually generates the content that are relevant and useful, and how do we correct that? So that's a very interesting question, and that is on the agenda right now for our next step of this research. But thank you. That's a very good question.
And Megan, do we have time for one more question?
Yes, I think we can do at least one more, maybe two, depending on the speed.
Okay.
Great question.
So we have a question from Max Liu. What's your views on the scalability of the system from domain to domain? Will we need to develop knowledge base for each domain / set of problems?
That is also another great question, which is a fundamental question in AI machine learning in general. I mean, you build this system for this task. You train this model basically on this data set with 16 different class labels. Can you transfer it? First of all, it is not necessarily generalizable. Transfer learning by itself is a whole area of research. Can you build an AI that can basically, for this particular example, for hand action recognition? Yes, and not yes, but my prediction is that very similar to what like large language models that we have, like pre-trained models will become a norm in the future. And then you have a pre-trained model for each particular domain. Right now, it's a pre-trained language model. We also have like vision models now. But we will have more specialized versions of these models that would then it would be easier than now to fine-tune those models, to tailor those models to your particular need. But that is right now, I mean, if you really want to apply this to another domain, you really need to annotate your own data set and retrain the model, if not modify it, at least retrain the model for your own use case. So in terms of scalability, that's an issue. In this particular case, what we've done is that we have created a data collection app that, for example, next researcher, they don't have to go through the tedious process of manually annotating that. We have built an AR app that you bring the subject, you put the headset, you provide some initial instructions, and then as they go through those process, it will generate an annotated data set for you, right? You can try to optimize it, you can try to make it more efficient, but that is certainly a challenge related to activity understanding for sure, for user modeling. Hopefully some of it is generalizable. And then for content generation, question answering, these are all very domain specific. And if you want to take this to another domain, the minimum thing is that you need to create your own data set and retrain the models. That's certainly a limitation.
I know we did not get to all of the questions. I'm sure more would trickle in if we were able to stay on longer, but I see it's just about 4 o'clock. So I'm gonna wrap us up there. But Mohsen, thank you so much for your time today and for sharing all of this with us. Just as we wrap up, just so that folks have this here, they want to know more. Our speaker series will continue later this term. So if you'd like to stay in touch with the Next Level Lab, you can visit our website, nextlevellab.gse.harvard.edu. You can also sign up for our quarterly newsletter there where we advertise events like this. So thank you so much, Mohsen, again, for joining us. Thanks to all of you for being here, and we hope to see you next time. Take care.
Thanks for having me. Thank you.